Hello everyone. Hope all of you guys are doing well. Then here we are for our chapter 25. Okay. Right. Let's see what we have here. So in this chapter we're going to learn about organic compounds and the atomic properties of carbon. Okay. So we will be learning about special nature of carbon and the characteristics of organic molecules, structures and classes of hydrocarbons, some important classes of organic reactions, and some properties and reactivities of common functional groups. Okay. Okay, let's look at some bonding properties of carbon. Carbon is like the fourth element in the periodic table. If you look at your periodic table in the second and the third period, carbon is the fourth one. So we have 1 to 8 elements. It's like the middle one, right? So carbon forms normally covalent bonds in all its elemental forms and compounds. It doesn't form ionic bonds. We can see the ground state electron configuration of carbon is helium is the noble gas prior to carbon, and then carbon is in the second period. So after helium comes 2s2, 2p2. So there are 4 valence electrons, 2 plus 2. The formation of carbon ion is therefore energetically unfavorable. If it is going to form an ionic bond, it has to make ions. So it has to either lose 4 electrons to make ion, you see, to make a noble gas configuration, or it has to gain 4 electrons. So it's in the middle. So it would basically try to form covalent bonds instead of making ions because it's not energetically favorable. Carbon has electronegativity value of 2.5. Again, that is also midway between that of most metals and nonmetals. So because of that also, carbon prefers to share electrons. Carbon exhibits catenation. So what is catenation? Which is the ability to bond to itself and form stable chain, ring and branched compounds. Carbon can bond with another carbon atom. Carbon-carbon chains can have large carbon atoms in a chain. So we call it as catenation. Okay. The small size of the carbon atom allows it to form short, strong bonds. The short carbon-carbon bond allows the ready formation of pi bonds. Remember the pi bonds? They form after the sigma bond, right? The pi bonds, you can have pi bonds in a double bond and a triple bonds. The short carbon-carbon bond allows the ready formation of pi bonds, increasing the variety of compounds that can be formed. We will look into these pi bonds again. Diversity and reactivity of organic molecules. Many organic compounds contain heteroatoms. So heteroatoms are atoms that are other than carbon and hydrogen. Mostly organic compounds are consist of carbon and hydrogen. When you have other atoms other than carbon and hydrogen, we call these are heteroatoms. The most common ones are oxygen, nitrogen and halogens. So what are the halogens? Halogens are the elements in the group 7, like your fluorine, chlorine, bromine, iodine. So they are your halogens. Most reactions involve the interaction of an electron-rich area in one molecule with electron-poor side in another. Carbon-carbon bonds and carbon-hydrogen bonds tend to be unreactive normally. If you take carbon-carbon bond or the carbon-hydrogen bonds, they are unreactive. Bonds between carbon and a heteroatom. What are the heteroatoms? Could be oxygen, nitrogen or halogens. When carbon bonds to one of these heteroatoms, it usually becomes polar because oxygen is more polar compared to carbon. Nitrogen and halogens, they are polar. So if the carbon bonds to any of the heteroatoms, so then the bond will become polar. That create an imbalance in electron density, and that provides a site for reactions to occur. That's how mostly organic compounds react. Heteroatoms and different bonding arrangements lead to great chemical diversity. You can see here, this is a carbon chain with 1, 2, 3, 4 carbons, and now you have oxygen heteroatom and hydrogen. So this is an alcohol. When you have OH group, that is an alcohol. Okay, now this is, the carbons are bonded one after the other. 4 carbons. You can have another compound where you have 4 carbons, 1, 2, 3, 4. But here one of the CH3 groups are connected to second carbon. That's again a different alcohol. Right? You can see it. These bonding arrangement give rise to chemical diversity. This is an alcohol, but this is a different alcohol. Now here's another one. You can have 1, 2, 3, 4 carbons and the 10 hydrogens all together, and now the OH group is in the middle carbon, and this carbon has 3 another carbon groups. Okay, and then you can have another one. The OH group is on this second carbon. You see, this is also has 1, 2, 3, 4 carbons and 10 hydrogens all together, but different arrangement. And here's another one. So you have 1, 2, 3, 4 carbons here, but you have less number of hydrogens here now, 2, 4, 6. With a carbon-oxygen double bond, a pi bond you have here. And here's another one. We have 1, 2, 3, 4 carbons, and you have oxygen in a ring structure, 3-membered ring. Here you can have a heteroatom with 4 carbons, and this is a 5-membered ring structure. And then oxygen could be in the center of these 2 carbons. Here's another arrangement of oxygen and the carbon, and this is called aldehyde functional group. This is another cyclic compound, cyclic ether, another cyclic compound. So you can see these heteroatoms and the different bonding arrangements where it bonds lead to great chemical diversity of the carbon containing compounds. Carbon skeletons. Each carbon atom can form a maximum of 4 bonds. Remember, carbon has S2p2 valence electron configuration, 4 electrons in the valence shell. So those 4 electrons can participate in covalent bonding, creating maximum of 4 bonds. Single bonds can rotate relatively freely, so there are often several different arrangements of a given carbon skeleton that are equivalent. So this is 1, 2, 3, 4 carbons. They are singly bonded, and these single bonds, they can rotate. Okay, so you can draw it like this, the 4 carbons, 1, 2, 3, 4, because carbon has 4 bonds. With 4 bonds, it has tetrahedral electronic and molecular geometry. So when you draw that, it's just showing carbons. This carbon has 4 bonds, 1, 2. What's not shown is the hydrogen. So there could be 2 hydrogens here. So you can draw it like this, the carbon skeleton. Now this 1, 2, 3, 4, which is same as this one, 1, 2, 3, 4. Because these bonds can rotate, you can bend it. Just by bending it doesn't make these are 2 different compounds. They are the same, since these bonds can be rotated. Here you have another carbon containing compound, 1, 2, 3, 4 carbons. Now this can rotate. Okay, so this is one arrangement. So by rotating another one, rotating one of the bonds, you can get this, but the connections is the same. You have 1 central carbon and 3 carbon, central carbon, 3 carbon. So they are basically the same, but these 2 are different. This one and this one different. This one and this one different. This one and this one different. Okay. These are some examples of 5 carbon skeletons. You can see 1, 2, 3, 4, 5, and then this also has 1, 2, 3, 4, 5, but this compound is different from this because one of the carbons are now attached to this second carbon. So they are not necessarily same compound, they are different. It's not just that you bend one of these bonds. Okay, here's another arrangement of 5 carbons. It's a different from these two. Central carbon, and you have 5. Here's another one. Now we have a double bond here. 1, 2, 3, 4, 5. Double bond at the end. Here you have the double bond in the middle carbon, 2 carbons. So these are 2 different compounds. Here you have the double bond in the terminal carbons, but with a branch of carbon. 1, 2, 3, 4, 5. So it's also a different compound. And here's another different one. Even though you have the same carbon-carbon connection here, double bond is between these 2 carbons. So that's a different molecule. And this one also different. So all 5 of these, even though they have 5 carbons, they are different compounds. Same thing here also. Okay, if you look at the connections, they are all different carbons. Different molecules of carbon. Drawing carbon skeletons. Each carbon atom can form maximum 4 bonds. So for these 4 bonds, you can have 4 single bonds. Like this. Let's say you have carbon, 1, 2, 3, 4. You can have 4 single bonds. Or you can have 1 double and 2 single bonds. You can have 1 double bond connected to the carbon. And then you can have 2 single bonds. So basically you have 4 bonds. Or you can have a triple bond. 1, 2, 3 and then another one. Like that. Okay. So can form 4 bonds. It could be the 4 single bonds. 1 double and 2 single. Or 1 triple and 1 single. Or you can have like this. 2 double bonds. Also another option. Carbon has 4 bonds now. Okay. The arrangement of carbon atoms determines the skeleton. So a straight chain and a bent chain represent the same skeleton. Remember the straight one we talk about? So this is a straight chain, and if you draw it like this, we just bent this bond. That these are the same, these two. Okay. Groups joined by a single bond can rotate freely. So a branch pointing down is same as the one pointing up. So this is pointing up. This is pointing down. So they are the same. Drawing hydrocarbons. Draw structures that have different atom arrangements for hydrocarbons with 6 carbon atoms. No multiple bonds and no rings. 6 carbon atoms. You can have 4 carbon atoms, 1 double bond and no rings. Let's say 6 carbon atoms. 6 carbon atoms, if you draw them straight, you can draw it like that. You can start 1 carbon, 1, 2, 3, 4, 5, 6. So each point represents a carbon, 1, 2, 3, 4, 5, 6. Now also you can draw 1, 2, 3, 4, 1, 2, 3, 4, 5 carbons, and you can put a branch that will making it 6. You can have another one like this. 1, 2, 3, 4, 5, 6. That's another one. Okay. Or you can have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you can have another one, 6, like that. Okay, that's a different one. So what else can we have? Let's see. You can have another one like that. 1, 1. Another one. All of these have 6 carbons. Okay. Okay, like this. 6 carbons, no rings. So here this one you have just straight chain carbon. 1, 2, 3, 4, 5, 6. I draw the shortened form in the previous one, but this is how it looks when you draw it with the carbons and the hydrogen. 6 carbons. And then you can have 5 carbon chain and one branch. 1, 2, 3, 4, 5 carbon, and then you put a branch on this carbon next to the last carbon. Or you can put another group carbon in the central one. Now the main carbon chain has 5 carbons and then a branch one. So these are two different ones because of the location of the branch. And then you can draw 4 carbon chains and 2 branches. So 1, 2, 3, 4. So you have 2 branches like this. One here, one here. And then you can draw 1, 2, 3, 4, 2 branches on 2 different carbons. Okay, that's another one. So those are the possibilities. 1, 2, 3, 4, 5. How many did I draw? 1, 2, 3, 4, 5. Yes, so the same things I have drawn here, that you can see the expanded form in the next slide. Okay. So the next one, 4 carbon atoms, 1 double bond and no ring. That we are going to draw structures with 4 carbon atoms with a 1 double bond. So this is 4 carbons, 1, 2, 3, 4 with a double bond. You can put the double bond in the center. And then remember we said carbon can have 4 bonds. So this carbon can have 1, 2, 3, 4. And then you have this carbon 1, 2, 3, 4. So you don't put another hydrogen here. If you do that, this carbon will end up having 5 carbons, which is not correct. So this carbon again has 1, 2, 3, 4. And this carbon 1, 2, 3, 4 like that. Okay. So this is the double bond in the center, and then you can put a double bond in the at the end. That's a different one. That's with 4 carbon, and then you can have 3 carbon chain and 1 branch. So 1, 2, 3 and with a branch. Okay. So those are the possibilities for 4 carbons, 1 double bond and no ring. And then the next one, 4 carbons, no multiple bonds and 1 ring. Okay. Okay. All right, you go back like this with 1 ring. 1, 2, 3, 4 carbons. So you put a 4-membered ring and then the hydrogens on it. And then here's another 3 carbon ring. 3 carbon ring. 1, 2, 3, 4. And in the ring has 3 carbons and 1 branch. Okay. Okay. Alkanes. So alkanes are the hydrocarbons that we say contain only carbon and hydrogen. Alkanes are hydrocarbons that contain only single bonds and are referred to as saturated hydrocarbons. So remember, you have heard this term saturated and unsaturated fat. So saturated means that has only single bonds. Okay. The general formula for an alkane is carbon. If you have n number of carbons, you will have hydrogen 2 times the number of carbon atoms plus 2, where n is any positive integer. That is the formula for alkanes. For example, you have an alkane with 4 carbons, then it would be C4. And then H would be 2 times N. 2 times 4 would be 8. And then the plus 2. 8 plus 2 will make it 10. So C4H10 is the alkane. Number of carbons 4, number of hydrogen 10. So alkanes has this general formula CnH2n plus 2. If it is C3, then hydrogens would be 3 times 2. 6 plus 2, 8. C3H8 like that. Okay. Alkanes comprise a homologous series, which is a group of compounds in which each member differs from the next by a CH2 group, homologous series. For example, if you take the first carbon 1, if you have only 1 carbon, number of hydrogen would be 2 times 1, 2 plus 2, CH4. And then the next one would be then C2H6. Next one C3H8. C4H10. So here each one differs by CH2 unit. CH2, different is CH2. Between these two, difference is CH2. Between these two, the difference is 1 carbon and 2 hydrogen. So we call, excuse me, we say alkanes comprise a homologous series group of compounds. Each member differs from the next one by a CH2 group. Naming organic compounds. How are we going to name? The name of any organic compound is comprised of 3 portions. You will have a prefix, root, and the suffix. We will see what are these. The root name of the compound is determined from the number of carbon atoms in the longest continuous chain. That is the root. How do we find the root name? You count the number of carbon atoms in the longest continuous chain and you choose the name based on that. The suffix indicates the type of the organic compound and is placed after the root. Suffix for alkane is "-ane". Alkane will end like "-ane". Okay, that's a suffix. Each prefix identifies a group attached to the main chain as well as its position. So these prefixes tells us if there are any other groups attached to the main carbon chain. Okay. So these are the root names for carbon and branches. If the number of carbon atoms 1, root name is methane. Meth. If it is an alkane, it would be then methane. If you have number of carbon atoms 2, your root name would be eth. If it is an alkane, then it would be ethane. 3 would be propane. 4, butane. 5, pentane. 6, hex. If it is an alkane, it would be hexane. And then the hept for 7, oct for 8, non for 9, dec for 10. And if these are alkanes, they would go like heptane, octane, nonane, decane. Okay. Rules for naming an organic compound. First thing is we choose the longest chain, longest continuous chain. So 1, 2, 3, 4, 5, 6. Okay, so that's the longest one. Find the longest continuous chain of the carbon atoms. Select the root that correspond to the number of carbon atoms in this chain. So if you have 6 carbon atoms, what is the root going to be? 6 carbon atoms, so the root going to be hex. Okay, and it has only single bonds, meaning it's an alkane. So then the name of the carbon chain is going to be hexane, hexane. Okay, that is "ane" is a suffix, hexane. Select the root, okay, we did that, and naming the compound type, which is a suffix. For alkanes, add the suffix "ane" to the chain root. Other suffixes appear in table 15.5 with their functional group and compound type. If the chain forms a ring, the name is preceded by cyclo. If it is a cyclic compound, we would say cyclohexane. Since it's no ring, we just say hexane. And you can also see in this hexane alkane, there is a branch or a group attached to this carbon. This group, and this group is attached to this carbon. They are going to be your prefixes, naming the branches or the prefixes. If the compound has no branches, the name consists only of the root and the suffix. Each branch name consists of a root indicating the number of carbon atoms and the ending YL, to signify that it is not part of the main chain. So here we have one carbon. What is the root name for one carbon? Meth. To indicate it's a group, instead of saying methane, we would add YL. So meth YL will make it methyl. If you have two carbons, the root name is eth. Since it's a branch, you would have to say ethyl. So this carbon, the second carbon, has two carbon group attached to it. So ethyl, one carbon meth, methyl. They are not methane and ethane. Since they are group attached to the main carbon chain, you have to represent it as methyl ethyl. Okay. And then these branch names comes before the root name. And we have to put them in alphabetical order. E comes before the M. So it would be ethyl methyl. Not necessarily how many carbons in the chain only by the alphabetical order. Ethyl methyl hexane. Now when you say ethyl methyl hexane, we know there is ethyl group on this chain and a methyl group, but we don't know where they are. So we have to put them to represent where they locate in the main chain. So to do that, we have to number the carbon chain. When you are numbering the carbon chain, there are two ways. Either you can start from here, 1, 2, 3, 4, 5, 6, or you can start from the end, 1, 2, 3, 4, 5, 6. So when we are numbering the main carbon chain, we always number so that these branches will get lower numbers. Okay, so if you come from here, it would be 1, 2, 3, 4. 4 and 5 positions will have methyl and ethyl. If you go from this side, 2 and 3 positions will have the branches. So you always choose such a way the branches would get lower numbers. Okay. To specify where a branch occurs along the chain, number the main chain carbon atoms consecutively, starting at the end closer to the first branch, to achieve the lowest numbers for all the branches. Precede each branch name with the number of the main chain carbon to which that branch is attached. So we have to say here then, there is ethyl and methyl. So ethyl comes first because the alphabetical order precedes the numbering order. Okay, so it's in the third carbon. So 3 ethyl, 2 methyl hexane is the name. Ways of depicting 3 ethyl, 2 methyl hexane. 3 ethyl, 2 methyl hexane is what we had named. Now let's see what are the ways that we can depict this structure. One way is this, which is the same, similar what you have seen in the previous one, or maybe expanded form. This is what you had seen. So this is called expanded form. You can see each carbon has 4 bonds and they are connected to hydrogen. So it's the expanded form. To make it simplify, you can write it the condensed formula, where instead of showing these bonds, you can say carbon with 3 hydrogens, CH3. Bonded to another carbon. This carbon has a H, this hydrogen, and CH3. And the third carbon has a hydrogen and CH2, CH3, like that, condensed formula. And then the most easy one is the carbon skeleton formula, where you are not showing carbon nor hydrogen, but you represent just the connectivity, just the bonds. So here you have a 1 carbon, this carbon here with 3 hydrogens, but you are not showing them. And this carbon has 1 hydrogen, hydrogens are not showing, and these points represent carbons. So this carbon, which is this one, has another methyl group, and this is connected to another carbon. So this is the carbon with 2 carbon groups, 1, 2, like that, and hydrogen not showing. And this carbon here connected to 1, 2, 3 carbons. 1, 2, 3. Carbon skeleton formula. And if you represent it in a ball and stick model, where if you have model sets, you put your carbons and hydrogen together. So this will how it look like. And this is called the space filling model. Because even though we say that there is a bond and then you have these atoms, they are very close proximity. You know, their van der Waals radii are overlapping. So you can see that's a space filling model. Okay, these are different ways that we can depict a molecule. Naming hydrocarbons. Give the systematic name for ABC of the following compounds. Now, what is the first thing we're going to do? We're going to find out the longest chain. So 1, 2, 3, 4. If you have 4 carbons, what is the root name? 4 carbons, root name is but, B-U-T. Since it's all of these are single bonds and it is an alkane, how do you name an alkane if it is but? Butane. Right? So that is butane. But is the root name and then the suffix is ane because it's an alkane, so butane. 1, 2, 3, 4. And then you have 2 groups, one here, one here. So that is a methyl group. One carbon is meth. Since it's a branch, it's methyl. Right? So there is a methyl group. There is a methyl group on the second carbon. So we have to specify how many methyl groups. Since there are 2, it should be then dimethyl. Right? But where are these 2 dimethyl groups are attached to? To the second carbon. So then you have to say 2,2-dimethyl carbon. 2,2-dimethyl butane. Right? So there are 2 methyl groups, 2 methyl groups. So then you would say 2,2-dimethyl butane. 2,2-dimethyl butane. Okay. Let me show you that. Okay, like here. 2,2-dimethyl butane. Okay. If we just say 2-dimethyl butane, that would not represent the correct compound. So it has to be 2,2-dimethyl butane. So the next one, B. First find the longest carbon chain. 1, 2, 3, 4, 5. That's 5. Longest continuous one. Do we have another one longer than 5? Let's see. 1, 2, 3, 4, 5, 6. You see here? This has 6 carbons. Continuous carbon chain. So that's going to be your longest carbon chain. Since it is 6, it should be hex. Since it's an alkane, then it should be hexane. Hexane. And then look at the prefixes to see the branches. So you can number them 1, 2, 3, 4, 5, 6. If you number like that, your branches comes to number 3 and number 4. 3 has a methyl group, 4 has a methyl group, 3 and 4. Let's try to number from the other way, starting this side. 1, 2, 3, 4, 5, 6. So your branches would end up being in the 3rd and the 4th position. So in that case, it doesn't matter which direction you start numbering. You would end up having your branches on the same positions. So you can choose either way. You can either choose the blue path or the red path to number. It doesn't matter. Okay, so we figured that it is a hexane. What are the groups that we have? 1, 2, 3. On the third carbon, we have a methyl group. 4, 5, 6. Fourth carbon also has a methyl group. So we have to say then 3, 4. You have 2 methyl groups. So 3, 4 dimethyl 3,4-dimethyl hexane. Okay, that's going to be the name of that.